Hello everyone, this is the penultimate chapter, that's chapter 12, and in this chapter we will be studying the reactions of carbonyl-containing compounds to synthesize alcohol-containing compounds. We will also be looking at how alcohols can be converted into some carbonyl-containing functional groups too. Let's take a look at the video breakdown now. In video 1 we will be looking at a new type of reaction mechanism known as nucleophilic addition. We will discuss the outcomes specifically of when hydride is used and when organometallic compounds are used in the next lecture. This is just an overview. In video 2 we will then discuss reduction reactions of carbonyl-containing functional groups, which will then be followed by the oxidation reactions of alcohols. We have until now discussed the electrophilic addition to double bonds. Now we will be discussing nucleophilic addition to a carbonyl-containing functional group. Nucleophilic additions do not happen to double bonds. The carbonyl group contains a particularly polar bond, which is also resonance stabilized. There is a large differential negative charge on the oxygen atom, making the carbon of the carbonyl group an electrophilic site. The highest occupied molecular orbital of the nucleophile will overlap with the lowest unoccupied molecular orbital of this electrophilic carbon, and a new sigma bond is formed between the nucleophile and the electrophilic carbon. Seeing as the nucleophile has been added and nothing left the original substrate, this is a nucleophilic addition reaction. The alkoxide is later protonated by acidic workup to afford an alcohol product. Let's discuss this further by thinking about the nucleophiles that are able to attack this electrophilic center of the carbonyl. One nucleophile used in nucleophilic addition reactions is the hydride anion, and this is H-. Sources of this hydride anion include two reagents, that's sodium borohydride and lithium aluminium hydride. We will discuss these in the next video in more detail. The other nucleophile, which is incredibly useful as it forms a carbon-carbon bond forming reaction, is the use of a carbanion or an organometallic reagent. In these compounds, the electronegativity of the metals are shown in relation to carbon. Seeing as the electronegativity of the metals are much less than that of carbon, this makes the R metal group place a large differential negative charge onto the carbon, thus making it a nucleophile. These compounds are known as organometallic reagents. Briefly, when the carbon is bonded to lithium, this is known as an organolithium reagent, and when the R group is connected to a magnesium, this accounts for one of the negative charges, but because magnesium is a divalent cation and therefore has an additional halogen, usually bromide, is attached, the name of this particular reagent is an organomagnesium reagent, but again these are more commonly named after the person who discovered their use. That's Victor Grignard, hence they are Grignard reagents.
This concludes part A.
In this video we will discuss the use of different reducing and oxidizing agents whilst revisiting the idea of chemoselectivity. Generally speaking, a reduction reaction is the reverse of an oxidation reaction. If you recall our discussion about oxidative cleavage, we said that oxidation increases the number of bonds carbon makes to an electronegative atom. The electronegative atom was oxygen for the purposes of that discussion. So a reduction reaction is one in which the molecule decreases the number of bonds made to oxygen and usually increases the hydrogen content. In the first reaction we observe the functional group conversion of a carboxylic acid to an aldehyde. In the second reaction we observe the reduction of an aldehyde to an alcohol. Note that the hydrogen content increase didn't occur in the first reaction, but the oxygen content did reduce, so this is reduction. In the second reaction, the oxygen content stayed the same, but the hydrogen content did increase. So this is also reduction, and hopefully makes clear the statement about usually increasing the hydrogen content or decreasing its oxygen content. The hydrogen represented in parentheses is a reducing agent, and these can be chemoselective. which means that certain functional groups like esters and carboxylic acids would be left unaffected by the weaker reducing agent, that's sodium borohydride. Lithium aluminium hydride, however, reduces all of the carbonyl functional groups seen on this slide. So, if we wanted to reduce an aldehyde, but not the aforementioned functional groups within the same molecule, then sodium borohydride would be used to cause this. We'll discuss the reason behind this chemoselectivity on a later slide. For now, a selection of reduction reactions are shown on the slide to give you an idea of what is possible. Take the time to pause the video and add these to your notes. The video proceeds to the next slide after 5 seconds. Here is the first of the two reducing agents. These are hydride anions that you will need to know for this course. This is lithium aluminium hydride. This particularly powerful reducing agent will always take a carboxylic acid, ester, aldehyde or ketone back to its corresponding alcohol. A ketone is always reduced to a secondary alcohol, while the aforementioned functional groups will always be reduced to primary alcohols. One point to note here is that you cannot use lithium aluminium hydride, aka LAH or LiFAL, in a protic solvent. This is because the hydride anion will always abstract the proton from that protic solvent, thus forming hydrogen gas. The reaction in itself is also very exothermic, so there is a chance that this could ignite and cause a fire. Therefore, when performing these reactions, an ether solvent is used. In the second step of the reaction, this is always going to be an acid workup. The purpose of this second step is to protonate the alkoxide intermediate that we saw in nucleophilic addition reaction mechanism of the last video. Sodium borohydride is a much less reactive hydride than LiFAL. This is capable of reducing aldehydes and ketones, but it will not have any effect on any esters nor carboxylic acids that are within the same molecule. Because of the reduced reactivity of sodium borohydride, these can be used in a protic solvent without the danger of the rapid buildup of hydrogen gas. The reaction mechanism is shown. The sigma bond between the hydrogen and the boron is nucleophilic, and it is this sigma bond that uses its electrons to form a bond with the carbonyl carbon. By nucleophilic addition, the carbonyl bond is broken and the electrons of the pi bond are placed onto the electronegative oxygen atom, and this is what gives the alkoxide intermediate. The alkoxide intermediate can then be protonated using an aqueous workup. Let's now summarize and explain the chemoselectivity for these two inorganic reducing agents. In summary, lithium aluminium hydride is not really chemoselective at all. It's going to reduce all of the carbonyl-containing species seen on this slide and to their fullest extent, i.e. all the way back to their corresponding alcohols. Sodium borohydride is chemoselective, and this means that if you have multiple functional groups within the same molecule, if those functional groups included esters and carboxylic acids, then it won't react with those. But within the same molecule, if there are any ketones or aldehydes present, then those will react. Now let's take a look at the reason for this. With respect to the lithium cation, this is a much better Lewis acid because of its small size compared to, say, sodium. In the first stage of the reaction, though this is left off in the previous slide, the carbonyl oxygen is able to form a dative covalent bond with lithium. And what this does is it pulls the electron density towards the oxygen of the carbonyl bond more so than the corresponding sodium cation would. Secondly, when the aluminium hydrogen bond is considered, the electronegativity of aluminium compared to boron is much different. This results in the aluminium hydrogen bond as being more polarized, whereas the boron hydrogen bond is less polarized. However, if we take a look at the relative position of aluminium and boron in the periodic table, aluminium is underneath boron, and so the aluminium hydrogen bond is in fact weaker, meaning that it's able to donate that hydride far more quickly. The boron hydrogen bond is much shorter and much stronger, and so therefore it behaves as a weaker reducing agent. So let's now take a look at the oxidation reactions of alcohols to their corresponding carbonyl-containing functional groups, and we will also consider the chemoselectivity of the oxidizing agents involved. So, as a brief recap, oxidation of an organic compound may be more broadly defined as a reaction that increases its content of any element that is more electronegative than carbon. For the purposes of our discussion, we'll be considering the second stage of the top reaction, whereby primary alcohols can be oxidized to aldehydes, this is known as partial oxidation, or can be fully oxidized to carboxylic acids. We'll discuss secondary and tertiary alcohols separately on the next slide. It is worth noting that primary alcohols are the only substrates that are capable of being partially oxidized to aldehydes or fully oxidized to give carboxylic acids. Secondary alcohols will always be converted to ketones by oxidation, but tertiary alcohols are incapable of any oxidation reaction for the reason discussed on the next slide. Although it is not necessary to know the mechanism for any of the oxidation reactions on this course, this is a useful aside in understanding why tertiary alcohols don't react. Alcohol oxidation usually occurs via an elimination reaction. Oxygen is able to use its lone pair to react with some oxidizing reagent that installs a leaving group on the alcohol's oxygen atom. The alcohol hydrogen and the A of that particular oxidant leaves. What's actually important though is the next step. In order for the carbonyl pi bond to form, a base is used to abstract an alpha hydrogen. This reacts to install the pi bond between the carbon and oxygen, thus giving the carbonyl group, and then the leaving group departs. And this is very similar to elimination mechanisms that we've studied earlier in the course. However, if you consider a tertiary alcohol, well, why won't this mechanism work? Pause the video and think about this for a moment. Resume when you have an answer. The answer is that a tertiary alcohol has no alpha hydrogens. The carbon containing the alcohol and that leaving group would be bound to 3 other carbons. So there's no alpha hydrogen to abstract, and therefore there is zero possibility of forming the carbonyl pi bond. Primary alcohols are really the only substrates that you have to be careful of, because these can be both partially oxidized or they can be fully oxidized. Now, if you want to stop with a partial oxidation, i.e. from a primary alcohol to an aldehyde, then you're going to need to use a specific oxidizing agent. In this case, we use the oxidizing agent known as PCC, which stands for pyridinium chlorochromate. The equation for its formation is shown at the bottom of the slide, and it's just really the reaction of chromium trioxide with hydrochloric acid and pyridine to give you the pyridinium chlorochromate salt. Now, this will also oxidize secondary alcohols to ketones, but that is the only option to begin with in terms of a secondary alcohol. Remember, that's only ever going to go to a ketone. But a stronger oxidizing agent, like for argument's sake potassium permanganate, under alkaline conditions will take a primary alcohol in the first step to an aldehyde, but this is something that is made in situ and is not easily isolable, and what usually happens is that the reaction pathway proceeds all the way up to the corresponding carboxylic acid. So let's take a look at these two reagents in a little bit more detail. There are two reactions on this slide which help to highlight the chemoselectivity of PCC versus potassium permanganate. So PCC is useful for synthesizing aldehydes, and it does not attack any pi bonds whatsoever. But if you remember, if you were to use potassium permanganate in base, then this will give you a carboxylic acid. But of course, if you look at the substrate presented here, it has a pi bond. And what would actually happen is that you would cleave that pi bond through oxidative cleavage, and though you would get the carboxylic acid, you would have also got an undesired reaction product or products from this. So I guess there's a question that results from this, which is, if you want to have a double bond in your molecule, yet you don't want to stop the reaction at an aldehyde, is there an oxidizing agent that will allow you to oxidize a primary alcohol all the way up to a carboxylic acid, but also contains a pi bond? Well, let's take a look on the next slide. Here is a third oxidizing reagent that can be used to address that problem. Chromic acid, that's H2CrO4, is prepared in situ by the reaction of sodium dichromate with sulfuric acid. And this is useful for the reaction of secondary alcohols to ketones, and also ensures the reaction of any primary alcohol to go to a carboxylic acid. But its real advantage is its chemoselectivity. This reagent does not react with alkenes. Chromic acid can also be formed by the addition of sulfuric acid to chromium trioxide, and this yields the reagent known as Jones's reagent after Ewart-Jones. Jones's reagent is chromium trioxide with a water acetone mixture. In any case, 3 equivalents of a secondary alcohol are needed, though typically 4 are used to form this chromic acid. The full redox reaction is shown, and 3 equivalents of the ketone are afforded. If we consider the last reaction, the use of sodium dichromate in sulfuric acid gives a ketone here, but had that alcohol been in the primary position, this would have given us the carboxylic acid. More importantly, the real take-home message here is to consider what would have happened to the alkene in this reaction at all. And the answer is, using Jones's reaction, nothing. But had we used potassium permanganate, that alkene would have undergone oxidative cleavage, and we wouldn't have got the desired product. Let's take a look at how this particular reagent works. Please note, you do not need to know the mechanism here, it's just a useful aside. In chromic acid, the oxidation number of chromium is +6, and this happens to be a clear orange-red solution. Once the primary or secondary alcohol is added, chromium is reduced to chromium 3+ ions, which provide an opaque green-blue solution. This colour change is a useful tool to organic chemists when monitoring the reaction and seeing whether any oxidation has taken place. In brief, the oxygen of the alcohol involved reacts with chromic acid to form a chromate ester by the loss of water. As discussed on an earlier slide, the oxygen of the original alcohol now has a leaving group, and the alpha hydrogen is exposed to show the second step. In that second step, oxidation by elimination occurs, whereby the alpha proton is removed by water. This kicks out the leaving group, which is responsible for the colour change that is associated with this reaction, i.e. H2CrO3.
This concludes Part B.